The number associated with a measurement is obtained using some measuring device. For example, consider the measurement of the volume of a liquid using a bullet. Notice that the meniscus of the liquid occurs at about 20.15 milliliters. This means that about 20.15 milliliters of liquid has been delivered from the burette. Note that we must estimate the last number of the volume reading by interpolating between the 0.1 milliliter marks. Since the last number is estimated, its value may be different if another person makes the same measurement. If 5 different people read the same volume, the results would be as follows. These results show that the first 3 numbers remain the same regardless of who makes the measurement. These are called certain digits. However, the digit to the right of the one must be estimated and therefore varies. It is called an uncertain digit. We customarily report a measurement by recording all the certain digits plus the first uncertain digit. In our example, it would not make any sense to try to record the volume in thousandths of a milliliter because the value for hundredths of a milliliter must be estimated using the burette. It is very important to realize that a measurement always has some degree of uncertainty. The uncertainty of a measurement depends on the precision of the measuring device. For example, using a bathroom scale, you might estimate the mass of a grapefruit to be approximately 1.5 pounds. Weighing the same grapefruit on a highly precise balance might produce a result of 1.476 pounds. In the first case, the uncertainty occurs at the tenths of a pound place. In the second case, the uncertainty occurs in the thousandths of a pound place. Suppose we weigh 2 similar grapefruits on the 2 devices and obtain the following results. Do the 2 grapefruits have the same mass? The answer depends on which set of results you consider. Thus, a conclusion based on a series of measurements depends on the certainty of those measurements. For this reason, it is important to indicate the uncertainty in any measurement. This is done by always recording the certain digits and the first uncertain digit. These numbers are called the significant figures of a measurement. The convention of significant figures automatically indicates something about the uncertainty in a measurement. The uncertainty in the last number is usually assumed to be plus or minus 1, unless otherwise indicated. For example, the measurement 1.86 kilograms may be taken to mean 1.86 plus or minus 0.01 kilograms. Solution. Even though the 2 volume measurements appear to be equal, they really convey different information. The quantity 25 milliliters means that the volume is between 24 milliliters and 26 milliliters, whereas the quantity 25.00 milliliters means that the volume is between 24.99 milliliters and 25.01 milliliters. The pipette measures volume with much greater precision than does the graduated cylinder. When making a measurement, it is important to record the results to the appropriate number of significant figures. For example, if a certain burette can be read to plus or minus 0.01 milliliters, you should record a reading of 25 milliliters as 25.00 milliliters, not 25 ml. This way, at some later time when you are using your results to do calculations, the uncertainty in the measurement will be known to you. 2 terms often used to describe the reliability of measurements are precision and accuracy. Although these words are frequently used interchangeably in everyday life, they have different meanings in the scientific context. Accuracy refers to the agreement of a particular value with the true value. Precision refers to the degree of agreement among several measurements of the same quantity. Precision reflects the reproducibility of a given type of measurement. The difference between the terms is illustrated by the results of the 3 darts thrown in figure 1.8. 2 different types of errors are illustrated in figure 1.8. A random error, also called an indeterminate error, means that a measurement has an equal probability of being high or low. This type of error is estimating the value of the last digit on a measurement. The second type of error is called systematic error, or determinative error. This type of error occurs in the same direction each time. It is always high or low. It indicates some large random errors, poor technique. Figure 1.8b indicates small random error but a large systematic error. And figure 1.8c indicates small random errors and no systematic error. In quantitative work, precision is often used as an indication of accuracy. We assume that the average of a series of precision measurements, which should be averaged out, the random errors because of their equal probability of being high or low, is accurate or close to the true value. However, this assumption is valid only if systematic errors are absent. Suppose we weigh a piece of brass 5 times on a very precise balance and obtain the following results. Normally, we would assume that the true mass of the piece of brass is very close to 2.486 grams, which is the average of the 5 results. However, the balance has a defect causing it to give a result that is inconsistent, that is consistently 1 gram too high, systematic error. Then the measured value of 2.486 grams would be seriously in error. The point here is that high precision among several measurements is an indication of accuracy only if systematic errors are absent.